Your coding agent can read files. It can search the repo. It can run tests, inspect errors, and make edits. But in a large codebase, that is still not enough. Because a real codebase is not just a folder full of text, it is a map of dependencies. One file imports another, one function calls another, one class implements an interface. A value enters through an environment variable, passes through 3 helper layers, and eventually reaches a database write. When a human senior engineer works in that repo, they are not just reading random files, they are navigating structure. Where is this symbol defined? Who calls it? What tests cover it? What else changes if this interface changes? Is this file generated? Is this module the public API, or just an internal helper? A coding agent that only has file search has to rediscover that map from fragments. That is the problem Codegraph-RAG is trying to solve. The concrete project here is called Codegraph-RAG. It parses a multi-language repository, builds a knowledge graph of the codebase, stores that graph in Memgraph, and exposes it to agents through a query layer and MCP server. But the important idea is bigger than one repo. For coding agents, retrieval should not just mean find chunks of text that look semantically similar. It should also mean recover the structure of the program. This matters because code is unusually hostile to naive RAG. In ordinary document retrieval, semantic similarity can get you pretty far. If a question asks about refund policy, a paragraph containing the words refund and policy is probably useful. Code does not always work like that. The function you need may not use the same words as the bug report. The test that matters may live in a separate package. The call site that breaks may be generated by a framework convention. The security issue may depend on a value flowing from an input parser to a shell command, even if those 2 files are textually unrelated. So, a vector database can retrieve plausible-looking snippets while missing the actual dependency path. That is why the right mental model is not just search, it is navigation. Codegraph-RAG starts by parsing source files with TreeSitter. TreeSitter is a parser framework that produces syntax trees for many programming languages. Instead of treating a Python file or a TypeScript file as plain text, the parser can identify functions, classes, methods, imports, modules, and other syntactic structures. Then the system turns those structures into graph nodes and edges. A file is a node. A module is a node. A class is a node. A function is a node. A method is a node. Imports become relationships. Calls become relationships. Definitions, references, class membership, package boundaries, and optional data flow edges become relationships. The result is a codebase that can be queried as a graph. Not show me chunks, similar to this sentence, but show me all callers of this function. Show me what imports this module. Show me where this class is defined. Show me what writes to this resource. Show me which files are in the neighborhood of this change. That difference sounds small until you imagine an agent making an edit. Suppose the agent needs to change an authentication helper. With normal file search, it might read the helper file, search for the helper name, inspect a few results, make a local edit, and run one test. Maybe that works. But if the helper is called through wrappers, re-exported from an index file, used by a background worker, and tested through integration tests in another package, the agent can miss the real blast radius. A code graph gives it a better first move. It can ask for the dependency neighborhood before editing. It can see callers. It can see imports. It can see related tests if the graph or naming conventions expose them. It can build an edit plan from structure rather than vibes. This is the same reason human engineers use IDE features like go to definition, find references, call hierarchy, and type navigation. Those tools are not cosmetic. They are the map. The difference is that agents need that map as a tool they can call. That is where MCP matters. The Model Context Protocol, lets external systems expose tools to agents in a standard way. Codegraph-RAG can run as an MCP server, which means an agent such as Claude Code can query the graph directly instead of relying on a human to open a separate dashboard. So the workflow becomes more mature. The agent receives a task. It queries the code graph. It identifies the relevant structural neighborhood. It retrieves the actual source for the nodes it needs. It proposes or applies a targeted edit. Then it runs tests and uses execution feedback to verify the change. That is much closer to how real software maintenance works. This also explains why the word RAG is starting to feel too broad. RAG originally meant Retrieval Augmented Generation. Pull in external information so the model does not have to answer from weights alone. But in practice, retrieval is not one thing. There is lexical retrieval, like BM25. There is vector retrieval with embeddings. There is graph retrieval. There is symbolic lookup. There is test execution. There are compiler errors, logs, traces, and type checkers. For coding agents, the best system is probably not one retrieval method. It is a routing layer over several forms of evidence. Use lexical search when exact names matter. Use semantic search when intent matters. Use a code graph when structure matters. Use the test runner when behavior matters. Use the compiler when types matter. A code graph is not a replacement for all of that. It is the missing structural layer. There is also a useful contrast with agentic search. A recent retrieval scaling study, BM25 wins at scale, found that file system agent search can work at small corpus sizes but becomes expensive and less reliable as the corpus grows. The lesson was not that agents should never reason. The lesson was that agents should not wander blindly through a large search space when a retrieval system can rank candidates globally first. The same lesson applies to code. Do not make the coding agent rediscover the repo structure by opening files one at a time. Build the map first. Then, let the agent reason over the map. Of course, code graphs have real limits. Static parsing does not perfectly understand every program. Dynamic dispatch is hard. Reflection is hard. Dependency injection can hide the actual call path. Framework conventions can create relationships that do not appear explicitly in the source. Generated code can pollute the graph. Build systems and runtime configuration matter. And, if the graph is stale, the agent may trust structure that is no longer true. Natural language to query is another failure point. If the agent asks the wrong graph question, a perfect graph will still give the wrong evidence. So the mature version is not graph equals truth. The mature version is graph equals one maintained evidence layer. It should be refreshed. It should respect, ignore rules. It should expose provenance. It should let the agent inspect source, not just summaries. And it should be checked against tests, types, and runtime behavior. That is why this belongs in the agent infrastructure stack. A chatbot can survive with a context window. A coding worker needs more. It needs a workspace where artifacts persist. It needs memory that does not grow into prompt debt. And it needs a map of the codebase so it can understand where a change actually lands. The next generation of coding agents will not just be better models dropped into larger prompts. They will be models connected to structured tools, file systems, memories, search indexes, code graphs, test harnesses, observability, and policy layers. Codegraph-RAG is one piece of that shift. It says, stop treating the repo like a bag of text. Treat it like a system. Because when an agent edits code, the question is not just what file looks relevant. The question is what the code is connected to. And if the agent cannot see those connections, it is not really navigating the codebase. It is wandering through it.